All right, so this will be the last series of problems for process controls. Here we have, so we're going to be focusing on transfer functions, more on how they work in series, how we can see, well, in this first problem, um, the amplitude ratios, which we derived in a previous video, how if we have a series of transfer functions that they are multiplicative, they are the product of two individual transfer functions, the phase lag being additive between two individual transfer functions if they're in series. We'll also see that the transfer function for a first order system approaches negative 90 degrees, and we can see two first order systems in series will yield an overdamped second order response. Um, so it's pretty similar to the second order, which I'll do here, even though it's not mentioned, just to kind of see the differences. I believe there's a peak we'll see, so we can see where the amplitude ratio has a peak, and that occurs at the natural frequency. So we'll find the angular frequency omega of our sinusoidal input that matches that natural frequency, so we can avoid that amplitude ratio going to infinity at that peak. And then we have phase lag and graphing the phase lag for pure time delay added onto a first order transfer function. So more in detail, just kind of overview. I kind of simplified everything. I mean, I kind of just read off the problem statement, but yeah, let's just kind of go into it. So we have our normal transfer functions, as we know. Can do this in kind of a block diagram algebra. So I don't know, G1 into G2. And as you know, something like G12, the product of those two, if we want the transfer function of the system of two first order, well, I guess it doesn't have to be first order, but two transfer functions in series, G12, it would just be the product, as we know, and as we've done in the past. So we'll do this in terms of real and imaginary numbers, just to kind of simplify things, and then we'll start plugging things in for the first order and the second order. So there'll be a lot of algebra today. So we know G1 and G2 break down into their real and imaginary parts. So that's R1 plus JI1, and then this is times R2 plus JI2. So again, nothing new. We've done this in the previous video where we derived those amplitude ratios and phase lags. So if we want the product, we'll just multiply across. So just distributing our variables here. And then we have j, we factor out a j, and we'll see that we have R1, I2, so something like R1 going to J1, I2, and I1 going to R2. So inevitably we'll have, we'll be adding these, right? Let's make sure I'm doing this correctly. So, maybe I'm trying to do it all in my head. I think it's easier if I just write it out like I'm used to. So J R1 I2 plus J, here we go, R2 I1, yep. And then we have plus, so there's J squared and then I1 I2. But we know J squared is -1, so that'll turn into a -1. Negative sign in front, and I'll just move this in front. So this is the product, and I can, of course, simplify, factor out that J in the middle. So J, and then R1 I2 plus R2 I1. Again, real and imaginary components, I just multiplied across. So that's our overall G12 transfer function. You'll use that notation. So if we want the amplitude ratio and phase lag, as I said, amplitude ratio is multiplying the individual transfer functions. So let's just show what it should be. So I take the real and imaginary parts for the amplitude ratio of 1 and 2. So we have our real parts and our imaginary parts here. And it was always the square root of, I'll just write the general form. It's square root of the real numbers squared and the imaginary numbers squared. So that would be, let's color code this. We have R1, R2 minus I1, I2 squared. And we have in blue plus I squared. So we just want our imaginary values. We don't take the j. J just denotes what the imaginary values are. So if we square that as well, R1, I2 plus R2, I1 squared. And we can do some more variable manipulation here. So see some things canceling out. Let's see here. So we have R1, R2, both of those are squared. It's minus 2 of, so you multiply the same thing twice, it would be R1, R2, I1, I2. And then I1, I2 times itself would be plus I1, I2, and both of those are squared. And yeah, I think that should be it for the left-hand side. And I guess I should have kept that in red. And then we have our blue. So kind of similar thing here. We have R1, I2 squared. Both of those are squared. And we have plus 2. And then it's actually the same thing, same middle term we got earlier. So you multiply it by this. It's arranged differently. So I'll write it how it's arranged. It'll look like that. But if they're just products of each other, if you can manipulate them, change the order, it's still the same. So these middle terms will actually cancel out. And then we have this last term, R2, I1. Both of those are squared. So this middle term cancels out, and we can simplify it to what it actually is. Kind of all the different arrangement of the terms that we can see. The R1s, R2s, I1s, and I2s. Then you have the different arrangements, like I said earlier. R1 squared. Again, all of these are squared because you multiply them against each other. The same value. All right, so that's what it should look like for our transfer function in series. So if we do it individually, we would have something like, so we had AR amplitude ratio 1 and 2. So we have AR1 times AR2, amplitude ratio of 2. And like I said earlier, those were the real and imaginary parts squared. So if I have for 1, it would be R1 squared plus I1 squared. And then this is times R2 squared plus I2 squared. And if we multiply these, you'll notice that this is pretty similar to our original product of the two transfer functions in series. I'm just distributing the variables across, and for what it's worth, I guess I'll write it out, since you can kind of see, well, you should see that these are identical, they're the same. So if I write out this this product, I have R1, R2 squared of each. I have R1 squared plus I2 squared. Oh, not plus, times I1 squared, or I2 squared. I have I1 R2 squared. Both of them are squared. And then I have the i's squared as well. And again, these two are the same. You can see each term, so R1, R2, R1, I2, R1, I2, I1, R2, I1, R2, and the two imaginaries. They're the same. Next up, we have the phase lag. So phase lag would be, how do we want to do this? So imaginary over, so let's just write it. We have phase lag phi, 1, 2 is the inverse tangent, arctangent, however you want to say, of the imaginary and the real. So I guess it's technically 1, 2. And we break that down further. We have our imaginary portion, the middle term here, the j's. So got a lot circled there. So this term without the j, so that's R1 I2 plus R2 I1. So R1 I2 plus I1. I guess I'll put imaginary first. So just the different combination. So that's our imaginary over our real, and that's just the outer term. So I actually wrote it right here without the squared. So that would be the real minus the imaginary. So the real minus the imaginary. And I believe that's it. That's what it should look like at the very end. So this will be using some trig identities. So for now, we'll start with saying that the phase of 1, 2 is equal to the phase of 1 plus the phase of 2. So if we do our little substitution, or not really substitution, but rewrite it, we have phi 1, 2 is equal to tangent. I want to write it this way. Yeah, sure. Tangent phi 1 plus phi 2. So at the end, you'll notice there's a tangent inverse in front. That'll be coming from the left-hand side since I'm writing it in terms of the tangent in front instead of the imaginary and real right now. So if we do some trig identities, so tangent, we know that is sine over cosine. Sine, phase 1 plus phase 2, phase lag, and then cosine, phase lag 1 plus phase lag 2. So these are actually something we've seen before. The are, I guess, trig addition identities. I don't know if it's worth trying to look this up. Since I'm pretty sure I know them off the top of my head, but why not? So trig addition. Oh, there we go. So yeah, a plus b, a minus b. So you'll notice that we had a phase lag. Let's see, split this and move this here and pull up this one full screen. So notice we had a phase 1 plus a phase 2, and on our, I guess, our Google search, we had a plus b and then cosine a plus b. So we'll be using those two. It's just the change between sine and cosine, and then cosine of the same minus sine of the two. Oh, I guess cosine of the two minus sine of the two. So go back. If I could do this. So it is cosine phi 1 sine phi 2 plus sine phi 1 times cosine phi 2. And I believe we've used the sine one before when we were deriving something in the previous video. Can't remember off the top of my head. And then cosine is cosine of both and minus sine of both. So these are trig identities. If you want, feel free to look up the derivation. I'm not going to try doing those now. So now that we have this, to simplify things further, we'll divide by this first term here. So I'll write the first term out on the denominator to show what it looks like. So you have cosine phi 1 sine phi 2 divided by cosine phi 1 cosine phi 2. And you'll notice that the cosine phi 1s cancel out, and you're left with this sine over cosine of phi 2. And all that means simply is that you have a tangent of phi 2. So the same thing will happen on the left side. We have sine phi 1, cosine phi 2, and the cosine phi 2s will cancel, so you have a tangent phi 1. Dividing the first term on the denominator by itself is 1. So I guess I can move it already here. And then minus, so we have sine of both divided by cosine of both, so that'll be a tangent of both phi 1 and phi 2. And from here, we can actually substitute our individual phases. So if you remember, we had tangent phi 1 is equal to imaginary over real, as well as tangent phi 2 imaginary over real. So that's all I'm substituting here. So we had tangent 2 at the top. Tangent 2 is I2 over R2. Tangent 1 is I1 over R1. 1 doesn't get any substitutions. And then you had tangent of both. So I1, I2 at the top, R1, R2 at the bottom. So just the products of the two. And now we're getting very close. All we need to do is multiply by this denominator, and we should have the exact same values as what we got earlier. So if you multiply by R1, R2 for the first term, and the numerator, we have I2, R1 plus, and then second term on the numerator, we have I1, R2. So the different imaginary and reals. Then R1, R2 by the 1 there in the denominator. And the denominator just canceled out for this second term. So this should be exactly what we got. So just a little bit different order with the imaginaries in front. But these two are actually the same. So the two different, I guess, combinations of the real and imaginary over the real minus the imaginary. And looks like, yeah, that's exactly what we got. So we just proved that for amplitude ratios, if they're transfer functions in series, the amplitude ratio is simply the product of the two amplitude ratios of the overall transfer function, I should say. And for the phase lag of transfer functions in series, that overall phase lag, that is the addition of two phase lags, given that those transfer functions are, of course, in series. So that makes us done with this first part here. Oh yeah, I forgot to mention, I have, I guess, I don't know, some inputs or something to help me if I get stuck. So I guess technically a hint. I think it's just inputs for code that I put in there. I honestly can't remember. But I shouldn't need it, or I don't think I need it. But the coding is pretty much near the end, so look forward to that. Again, more of the algebra here, so we'll be doing the first order system. So prove that it approaches 90 degrees, so that's the phase lag. And if you remember our function for, well, phase lag, we've done it already right here. It's using the tangent function. And of course, tangent goes from negative pi over 2 to pi over 2. However, we are, well, you'll see at the end, I'm kind of spoiling it here, but we'll have two positive constant, or not constants, but two positive inputs to our tangent function, resulting it in going only from 0 to pi over 2, and of course, a negative sign in front, so it'll be 0 to negative pi over 2. So that is why we're talking about negative 90 degrees in that regard. So I'll write that out here. So tangent x, we know, goes from negative pi over 2 to pi over 2. So that's the domain if you'll use parentheses, since there's asymptotes at those values. And since it's only in one quadrant, since our inputs were positive, well, I guess you'll see it later, it'll actually be 0 to pi over 2 for positive numbers. Or integers, I don't know, I guess numbers or values. And then another definition or I guess, yeah, definition is, I guess, is a better word for an odd function. We have, so f of negative x, that's tangent, is equal to negative f of x. So this is the definition of a odd function. It's symmetric across the origin, given you do, I think it's a 180 degrees flip. So just to give some more visuals here, because why not? I don't know. Trig, did I type in last time? Tangent x graph. There you go. Pi over 2. I mean, hopefully this makes sense. So the asymptotes approaching pi over 2 and negative pi over 2, and we're positive, so we only look at this upper quadrant. All right. Back. Okay. So we start with our first order transfer function. Here we're recording. Awesome. Okay. So our first order transfer function, the general form, we have k over tau s plus 1. And we'll be seeing this a lot where we do two things. The first step is with our general form. We do a substitution for s equals j omega, and this is to get it into our angular, or I guess just the frequency domain. It makes it easier to analyze it in terms of sinusoidal inputs. And it's exactly what we did in the previous video for, I believe, the last set of problems for controls, process controls. So if we do, I'll just put the k out, we have 1, and then tau j omega plus 1. Now the next step here is kind of unorthodox, but we usually use it when the complex number is in the denominator. So this is algebra. We're going to be multiplying by the complex conjugate of the denominator, or I guess the just a complex number, so just a conjugate. In this case, I'll move the 1 in front so it looks better. It'll be 1 minus tau j omega. Remember, we just inverse the sign in front of the imaginary. So it's always real plus imaginary for complex numbers. Here, the real portion is 1, imaginary is tau j omega. So if we multiply by 1 minus tau j omega, we have, so I guess mult by conjugate, and we have k, so 1 minus tau j omega up top, and the denominator we multiply, so we multiply all of it since it's equivalent to multiplying by 1. We multiply across all terms, and then remember, this follows the same format. If you remember box method, we have a plus b and a minus b. So the two a terms and b terms get multiplied, but you'll notice these other terms on the diagonal, or I guess what I circled in pink, those get canceled out. So we're left with a squared and negative b squared. So we have a squared. In our case, a is 1, right? Did I do that right? Yep. We have 1. And then we have tau j omega squared. And we know that this should be, I'll just write out this portion for the denominator. So negative, I'll put that in, tau squared, j squared. Well, you see where I'm going with this, omega squared, and j squared, of course, we know is j root negative 1. So this negative becomes a positive, and then we have tau squared, omega squared. So what we're left with is k 1 minus tau j omega at the top, and 1 plus tau squared omega squared. So now that we have that, we can do our amplitude ratio. So that will be amplitude ratio. Remember, it's real over square root of the real value squared plus the imaginary value squared. And remember, we have a k in front. So I'll write it out now explicitly, but I'll kind of simplify things to make things go faster later on. So the real portion, we have the 1 over the denominator. So we have 1 over, what was that, 1 plus tau squared? I don't know why this is red. 1 plus tau squared omega squared. And this is all squared. And that is plus the imaginary term. So the imaginary term has a negative sign, but that will also be squared, so it'll end up being positive. And we don't take the j, since that just denotes that that's what the imaginary term is. So we have, what is that? Negative tau omega over 1 plus tau squared, omega squared. All of that is squared. So you'll notice that the denominator for both of these terms is in fact being squared and square rooted, and we can actually add the terms up top and kept them in the same form we had over here at the end of our substitution and multiplying by the complex conjugate. So we can actually factor out that denominator, so it becomes something like k over, maybe I'll keep the k out. So it'll be k over, I'll evaluate the square for the 1, so that's just 1. And then for the second term, tau omega negative, so that's tau squared plus tau squared omega squared. That's all over the denominator, which got factored out since it was being square rooted and squared. So that's 1 plus tau squared omega squared. And notice that these two terms are actually the same. And if you remember, just simplifying, I know it looks a little different right now, but something like x to the 1/2 divided by x, that just gives you x to the negative 1/2. In our case, x is this term here. So we subtract the exponents, so we're left with k 1 plus tau squared omega squared, all of that to the negative 1/2 power. And that's our amplitude ratio. So that'll be important later on when we do two transfer functions in series. I guess first order. I don't even know if that's part of the question, but I'm just going to show it anyway. So that's amplitude ratio. I actually don't think this is even a problem, but now we actually get to the phase lag, which is what we're worried about or concerned about. So this would be the imaginary over the real and arctangent of that. So what is the imaginary over the real? I'll write it explicitly again. So that was 1 over the 1 plus tau squared, omega squared, then over the imaginary portion. So right here, we have negative tau squared. Well, that's being squared. So I guess it's just negative tau omega. So negative tau omega over the same denominator. And of course, with multiple fractions, we can multiply by the reciprocal of the denominator, something like this. So really quickly, I won't even write out the denominator. So multiply by the reciprocal. You have the denominator up top now, and then the negative tau omega. So did I do that right? Oh, it's imaginary over real. I don't know why I wrote real over imaginary. So negative tau omega, and then 1. So just flip them, since again, phase lag is imaginary over the real component, and I just flipped them by accident. So I guess I should change this as well. This should be negative tau omega, and then 1, so just negative tau omega. So now we see that the phase lag is equal to the arctangent of negative tau omega. And now here's where that odd function definition comes in. We have the negative sign, and again, f of x as a, not f of s, f of negative x. It's the same thing for an odd function, negative f of x. Again, remember that tangent graph, it was symmetrical about the origin. So something like, if I could do a good job here, it was negative, or pi over 2, and negative pi over 2. So this would actually be tangent, negative tangent, arctangent of tau omega. And now, since we're normally given positive values, we would think we're here, but we have the negative sign in front. We're actually in the negative quadrant. Both of them are negative. And since we're only given positive inputs, it would go from 0 to negative pi over 2 in radians, which would be 0 to negative 90 degrees in degrees. So converting, again, pretty simple, but pi over 2, 180 over pi, the conversion. So that's just 90. Pi's cancel out. 180 over 2 is 90 degrees. So that is our domain range. And if you remember in the last video for transfer functions and this idea of amplitude ratio and phase lags, we've seen this negative 90 degrees. We're actually going down to 3 tanks in series. So this actually went to 270 degrees. And if you remember what I said about phase lags being additive, so if we were to do, I guess 1, 2, 3 in a row, we would have phase 1 plus phase 2 plus phase 3. And remember, our series of tanks were all first order transfer functions. We would have negative 90 degrees here at the end, negative 90 degrees for each actually, and they actually would all add up to negative 270 degrees. So that was the same thing as doing negative tangent, negative 1 over, and these taus don't have to be the same, neither do the frequencies. So I'm actually subtracting them. That's why we got negative. I don't know why I changed color. So that would be subtracting the tangent 3 times effectively. And I don't know if we use the same tau, but they can be different taus. So this is the same thing as what we did before in 3 tanks. And you'll actually see that since it only reaches 90 degrees for first order transfer function, and actually also for the second order, or not second order, but 2 first order transfer functions in series, they only reach negative 90 and negative 180 degrees respectively for the first order transfer function by itself, and then in series with 2 first orders. So they actually are, the first one's negative 90 degrees, so we actually don't reach the 180 degrees condition to, well, when our system becomes unstable. And then for the 2 in a row, the 2 series, it reaches negative 180. However, that's an asymptote, since remember, for tangent, it goes to infinity at its domain limit, I guess. So while it does reach negative 180, it never actually touches it. It's an asymptote. So it actually doesn't have an unstable value there. And remember, this is for, we were using a proportional controller for the tanks in series. So no matter how many, we could add a KC for our original transfer function up here. So we just multiply by KC, and well, KC is, well, phase lag, since we'd have to consider it, technically, since it's its own transfer function of kc, that's the imaginary over the real. And the only real version of that, since there's no imaginary values, it's just kc, well, there's no phase lag. So when you include the kc into this expression of the three, or I guess technically 2 and 1 first order transfer functions in series, you wouldn't have to add an additional phase lag. It would be whatever domain so the first order transfer functions are in. So the transfer functions, I guess the first order transfer functions are here what dictate that limit of stability. In our case, as we've seen, for first order by itself and first order in series with just 2, they will never reach that 180 degrees that we were trying very hard to not reach. And I'll actually graph that later on so I can stay on the iPad, and then I can completely shift to the coding later on. So yeah, I think that's all I want to say for that. So I'll show this later. So just kind of keep that in mind when I show that in collab with our Python code. I think we're done for the negative 90 degrees here. So that's cool. Next will be 2 first order systems in series, and that's analogous to a second order system. Sorry, I think my voice is giving out here. Okay. So, I don't know if it's worth doing. I guess I could show what the second order looks like, if I remember correctly here. So, the second order transfer function comes about. I don't think we've done this before. In class, we were shown that it is the Laplace transform of a second order differential. So I think it's tau squared. So second order, dt plus 2 zeta, our dampening factor variable. I forget what it's called. The exact name anyway. So that's 2 zeta theta. I think that's it. And omega, maybe. Am I forgetting something? Or no, the omega comes from the s. So then we have just first order differential plus 1 times y. So that's just y. And then that is equal to k, our system gain, and well, that's the relationship of our output to our input, and then times u as some forcing function. And the Laplace of that is what we get for our second order transfer function. So we take the k in front. Well, I like to, since we're going to do some manipulation here later on, actually. And the differential variables kind of show where the s for the Laplace domain come from. So it'll actually be tau squared s squared plus 2 zeta tau, and then that times s plus, and then just not s but 1. So that's our second order transfer function general form. And again, that comes from our second order differential equation, taking the Laplace of that. So this is what we'll use to reference for our I don't know, 2 first order. I guess I should use the word 2 first order transfer function in series. So that's what we'll be doing right now, and I believe we're going to prove that it's always overdamped. So this idea of dampening that, that zeta, that dampening factor, so that we have 3 different values we can come to for zeta. Typically it's underdamped, critically damped, and did I say underdamped? So underdamped, critically damped, and overdamped. Overdamped is when so it's greater than 1, zeta is greater than 1, and it comes to that equilibrium or steady state slower than it would be if it was critically damped. Critically damped, oh, I'm sorry. So for, overdamped, it's right as I just said it was, but the only thing is that it does not have a oscillatory motion. So it would come down gradually decreasing, but slower than it would be if it was critically damped. Critically damped does the same thing, but just faster than overdamped. It comes down to that steady state gradually, and it kind of is the border. So yeah, it's the border between oscillatory motion and non-oscillatory motion. Zeta equals 1 for critically damped. I think I forgot to mention that. And then for underdamped, we have zeta is less than 1, and that is when it has oscillatory behavior, but it also decreases with amplitude in time. So I guess I don't know why I was saying it. I could have just said it here or wrote it out. So we have what I said in order, greater than 1, equal to 1, and less than 1. So this is overdamped. Have critically damped. And then underdamp. And we'll see that for our case, this zeta value will affect where we see the peak of our second order transfer function, and that peak is where our system would inevitably blow up to infinity when our omega, which is analogous to our sinusoidal input, is matching or resonating with the natural frequency of our system. That is when the amplitude ratio hits a peak. So we'll see that later on after I do this, where and right now we're going to be doing two transfer functions, our first order transfer function in series. So we're going to try to relate this to our second order, and then I can go on more about that peak I was mentioning earlier. So in series we would have, let's do k1 tau s, tau 1 s. So these don't have to be the same k's and taus, even though we made them the same. I don't know why I did a plus. Even though we made them the same in our previous examples. So yeah, we want to do what we normally do. This is the product of two transfer functions in series. So I'd be multiplying. Oh, I forgot a plus one. What am I doing? So I'd multiply the denominator. So that would be tau 1 times tau 2 s squared plus, I'll factor out a s, and it would be tau 1 tau 2 s, tau 1 plus tau 2, I should say. I always make that mistake. Tau 1 plus tau 2. And then just 1. Right. Pretty sure. So tau 1s times 2s squared, and then tau 1s plus 1, tau 2s plus 1, factor out a s, and then 1 times 1. Perfect. So we do our usual steps that I mentioned before. S equals j omega to get into the frequency domain. So k1, k2. So we have, I'll put the 1 in front. Since we have s squared, we know the j squared becomes negative. So this first term becomes, let's see, plus j squared omega squared tau 1 tau 2. And this j is a negative 1. So I'll make it 1 minus all of that. And second term, we have just j omega, tau 1 plus tau 2, and the 1 I moved in front. Here's where it gets a little wonky. We have the multiplied by the complex conjugate. So multiply conjugate. And for this one, it would be, so we have our real and we have our imaginary. So we just change the sign in front of the imaginary. And that would be, let me just write it out here. 1 minus omega squared tau 1 tau 2 minus a j omega tau 1 plus tau 2. And remember, when we multiply by the complex conjugate, we have a plus b, a minus b. Again, the different terms between the two cancel out, so we have negative ba and ba. Those get canceled, and we just have to worry about a squared and b squared, the two different components being squared. So that would be, this is our a, and this is our b. So that being said, this denominator should just be the top squared. So I don't think it's worth trying to square that now. And then now we have our b term squared. It's b positive, or I guess negative b squared. But remember we have a j squared, so I'll write it and then I'll simplify it. So it'd be minus, we square up our terms here. Square up, okay. And then this j squared becomes a negative, so we negate that negative, making it a positive. Positive. Now, I think we're done, right? Actually, I don't think I even need to do this, right? Since the whole point is to relate, yeah, I don't know why I'm doing this. The whole point is to relate the first order transfer function to the second order. So I actually got ahead of myself. I was thinking we were doing the second order. Sorry about that. So now we relate these two, is what I was trying to say earlier before I got carried away, started doing something I wasn't supposed to. So we relate each term in the denominator and also our k1, k2 to the k. So first we have our k, that's pretty easy, that's k1, k2. Next we have that tau squared. Remember the s squared is that substitution for j omega. Do I actually need to substitute j omega here? Let's see. That's right, 2 zeta j omega. Yeah, I don't think I need to, right? So since the first one will be tau squared, come off, okay, yeah, tau squared equal to tau 1, tau 2. And this is called the geometric mean when we take the product of the two and take the square root. So I just moved the square to a square root, took the square root of both sides essentially. Second term is this 2 zeta tau, and that's related to this tau 1 plus tau 2. So to isolate this 2 zeta, we divide by tau, and we know that to be up here, tau 1 square root tau 1 tau 2. So tau 1 plus tau 2 divided by square root tau 1 tau 2. So that is equal to 2 zeta. And what we're trying to say is that this zeta value, I'm just going to rewrite this, is overdamped. Always greater than 1, as I mentioned before for zeta. So zeta greater than 1, that means it's overdamped. It's going to come down gradually, slower than it would for a critically damped system. So if I can square root this or square it, yeah, I'll square it. So I'll rewrite it first. So 2 zeta is equal to tau 1 plus tau 2 square root. So this is the geometric mean, square root and product. Now I square these. So we have 4 zeta squared equal to tau 1 plus tau 2 squared over tau 1, 2, tau 1 and tau 2. And this is always greater than 1. And typically, you could just stop here technically and just say, well, the time constants tau 1 and tau 2 are always positive. So this value has to be always positive for this zeta value, I should say, is always greater than 1, given that tau 1 and tau 2 are I should say, positive values, since time constants, again, tau, the time constant, measures how a system reacts to, or how fast a system reacts to a given input. So a larger tau would mean a slower reaction to reaching its final output. And I believe the percentage is like, so the time constant is how long it takes to reach like 63.2 or percent, I believe. So some value, and it's measuring how fast it reaches that value, a percentage of the final output, I should say. So to prove that, we'll move it over and do some manipulation. So we don't really care about the zeta squared, we care about this 4. So I'll do something like 1 and then rewrite everything. So tau 2 squared divided by 4 tau 1 tau 2. And we can actually expand this numerator. I'll do two things at once. I'll move this over and then I'll expand the numerator. So it would be 4 tau 1 tau 2 greater than, and then it would be tau 1 squared plus 2 tau 1 2 tau 1 2. Yep. So 2 tau 1 2 tau 1 tau 2, I should say, plus tau 2 squared. Now these terms are similar. We subtract, so we have 0 is greater than tau 1 squared minus 2 tau 1 2 tau 2 plus tau 2 squared, and this is just a simplification of square difference of squares. I think that's the right term. So I don't know why I squared that. Tau 1 minus tau 2 square. So that would, these are the same. And if you'll notice, for any values of tau 1, tau 2, all they're positive, but even if they were negative, If they're squared, anything squared is greater than 0. So this means that this zeta value has to be greater than 1. And for two first order transfer functions in series, which is what we wrote here, it is always the zeta value is greater than 1, so it has to be overdamped. So I think that was the third thing here. Series will be overdamped for a second order. Yep. So we related that to the second order and then did some manipulation with an inequality. Or yeah, inequality. And now I'll actually do something that's not listed here, but I think it'd be kind of interesting to see. This second order transfer function. So I'll do that substitution for s equals j omega. I'll multiply by the complex conjugate so we can see the amplitude ratios and the phase lags of this system. I'll spoil it now. It's second order, so it's actually two first order transfer functions in series. So that phase lag, as we mentioned over here, will only reach that 2. So it's 2 negative 90 degrees. So it'd be negative 180 degrees, and it'd be asymptotic. Is that the word for at negative 180 degrees? So it'd actually not be unstable. Also, the amplitude ratio will have this peak that you'll see since we have this zeta value controlling whether or not the amplitude ratio or the derivative of the amplitude ratio goes to 0. So again, that omega value is analogous to a sinusoidal input, and if that sinusoidal input matches the natural frequency, given that our zeta is 0 and it's there's no dampening factor at all, which is not the case. If the sinusoidal input is resonating with the natural frequency of our system, then the amplitude ratio reaches a max. And we want to avoid that. So what we do, we kind of go backwards. We start with the amplitude ratio, find the peak, and then find what angular frequency or of our sinusoidal input will give us that amplitude ratio max. So we can avoid that and kind of tune our bounds. If that makes sense. So I don't know if it's worth. Yeah, I might just copy paste this, honestly, so I don't have to memorize this thing. Oh, where did we go? Down here. So copy paste, right? And I'll do it on this side here. Guess it's now white. So let me. There we go. Now we can move here a little bit, maybe. Come on, there you go. Yeah, it gets stuck a little bit if don't have anything over there. Okay, so now update. Going to do our normal steps. Have anything underneath? Perfect. So first step, get into the angular frequency main. So we just have k, just substituting. So this s squared again will be j squared. So we know it's negative. I'm gonna bring the 1 in front. I'm gonna do what I was doing earlier, but now it'll lead to something this time. So we have 1 minus, and then it was j omega here, j omega squared. So j squared went away since this negative sign here, and now we have omega squared, so tau squared, omega squared. And then plus, this will be our imaginary portion, as you'll see when we substitute j omega for this s. I'll just put it in front, j omega 2 zeta tau. Should be good. And then 1, of course, at the top. Second step, complex conjugate. Here's where it gets a little dicey, so we'll see if I get this correct. The mults by conjugate. K in front, still there. Real, so this is real minus, or real plus imaginary. So for the conjugate, it'd be real minus imaginary. So 1 minus tau squared omega squared minus j omega 2 zeta tau. Did I do that right? So omega 2. Yep. Okay. And it's over. So now we multiply them, and now here's where that difference of square, well, not difference of squares, but that box method I was talking about earlier, we only have to care about the squares of the a and b terms, since the BA terms will cancel out. This is actually negative. So we worry about this is our a and this is our b. In our case, it shows negative b squared here, but this imaginary will make it plus b squared. So we'll see we have 1 minus tau squared omega squared squared. And then we have normally j squared omega squared Now 4 zeta squared tau squared. However, this j squared is -1, so we have minus. Did I do that right? Huh. I don't know if I did that right. So it's normally, it would normally be negative. I'm sorry. It'd normally be negative, and then it's j squared. Since we have negative b squared, like I was saying earlier, it's normally negative, but then the j squared makes it positive here. So there we go. Plus, it should be. There we go. Now we do the amplitude ratio. So amplitude ratio, that was square root of r squared real over real squared. Oh my god, I'm just gonna write it. My words are failing me right now. So it was real squared plus imaginary squared. So applying that to our system, we have k real, and I'm only going to write the numerator, since remember for the denominator we did this before, where the denominator came out on the bottom. Right here it was squared and square rooted right there, so we can just take that out, factor that out. Where are we? So I guess I'll write that at the bottom now. We have 1 minus tau squared omega squared squared plus omega squared, I guess 4 in front, why not, zeta squared tau squared. Now we're squaring the difference of these two up top. We have 1 minus tau squared omega squared squared plus, so I guess it's technically negative, but it gets squared anyway. So we know that's going to be just copying it down this and squaring it, honestly. So it's squared, and then this is a positive. Did I do that right? Yeah, because we squared the -1. So it becomes plus. There we go. Yeah, and you'll notice that these are actually the same again. So this simplifies down to k 1 minus tau squared omega squared squared plus 4 omega squared zeta squared tau squared. I'm going to bracket and then -1/2. So that's our amplitude ratio. I won't bother with the phase lag since we already know it's, I mentioned earlier, this is a second order, is just 2 first orders in series. We know for 2 first orders, like we showed, where did we show that? Up here. That's just 2 -90 degrees subtracted from each other. So that we only reach -180 degrees, and you'll see that when we code this. So I'll actually code and then come back for the last part of the set of problems. So if we want that peak I was saying earlier, the peak of this amplitude ratio, so again, that's where we have a peak where the resonance frequency, I guess the natural frequency, resonates with the sinusoidal input and creates that amplitude ratio blowing up to infinity. So if we want that peak, we have to get the derivative of our amplitude ratio with respect to omega, our angular frequency, and it has to be 0. So we have to take the derivative of our amplitude ratio here. So remember, derivative of an exponential, here we go, like so. It's just bring down the exponent and then subtract 1. So I'll bring down the exponent, that's -k 1/2, -k over 2, and we take it to the n-1. So that's the same thing as writing -3/2. So I'll just do that actually. I'll write it at the bottom so it doesn't get too clustered, I guess. So -1/2 minus 1, that's -3/2. So I just rewrite the whole thing for wow, my voice, for -3/2, which I could just write as +3/2 in the denominator, so we don't have so many terms in the numerator. So bracket that, and this will be 3/2. Now, chain rule, we have to do the derivative of our numerator. So that would be starting from this term, we have bringing down the 2 in front. Then we have our original, I guess, I don't know, function or variables. I could write this. All right, and then we have the derivative inside. So it's something like f of u is equal to I don't know, f of u, and maybe that would make more sense. F of u squared maybe is 2u, and did I do this correctly? U of m maybe is this inside portion. So 1 minus tau squared omega squared. I guess this is technically a derivative. If I did the derivative there. And this would be derivative of u. I don't know if I'm overcomplicating this. And it's that, so it would be derivative of that. And that is, so 1 goes away and you have negative 2 tau squared omega. So that's just negative 2 tau squared omega. For that, a little clunky or clustered. Next term we have, pretty simple. Omega is only 2 squared. Well, there's only 1 omega, I should say. So that's just 2 times 4, it would be 8. Then omega by itself, and then the constants kept the same. Cool. Hopefully you did that right. Now we are wanting this to go to 0. So you don't want to have a divide by 0, so we don't really care about the denominator. So what we're looking at here is the numerator. How does this go to 0? So we can factor out, actually, I think this term completely, almost. I think since this is 8 and we have negative 2 and 2, we'll factor out a 4. So I'll just write that. No, factoring, maybe. Factoring numerator. So I'll factor out this term in the middle. I circled in green, so we have a 4. And then tau squared omega. So if you factor from the first term, the 4 is out, so all we have is 1 minus, come on, 1 minus tau squared omega squared. However, we have a negative sign in front, or I guess here, since we're factoring out this middle term, and then we have the negative sign. So I can apply that by doing something like this, maybe. Put it out front. Then we have the 8, but that we factor out a 4, so it becomes 2. We factor out omega, so that's gone. Tau squared, that's gone, so it's just zeta squared. And notice that this is negative plus a positive, so I could just rewrite it as this. 2 zeta squared minus 1 minus tau squared omega squared. Now, we don't really care about this constant, so we care about these two. How do these terms go to 0? So one way I mentioned earlier, if we had no dampening. So again, what I mentioned earlier about sinusoidal input matching the natural frequency, that is for if dampening is 0, then we'll have that peak. So if dampening is 0, zeta is 0. So if zeta is 0, what is happening? If zeta is equal to 0, then we just have this portion. How does this go to 0? Then we have 1 minus tau squared omega squared must be equal to 0. Well, omega has to be 1 over tau. If that's the case, we would have 1 minus tau squared 1 minus over tau squared, so that would be 1 minus 1, and that's 0. So if theta is equal to 0 and our omega, our angular frequency, our sinusoidal input has a frequency of 1 over tau, then AR will reach its max. So AR is max. So that's the peak I was talking about. And to avoid that peak for this second order transfer function, we went backwards, or we're going to go backwards, I should say. I'll code this out really quick. It would be kind of just copy pasting, just putting in the transfer function. Make sure it's in the frequency domain. So sub in s equals j omega. And then we would see a peak. So honestly, let's just do that. Good, we're at 1 hour, fine. So let's go back here. Music. Anyway, let's run this. So this is just our last video where we did stability analysis, the Bode diagram, how it matched our transfer functions. And all I will be doing is kind of copy pasting it, really. So this was our real and imaginary, our transfer functions, and I'll do this with second order real right here. And I think this is where I was kind of forgetting what to put for the inputs. I believe we put k is 1. We don't have a controller here. This is just second order. I guess I can put that second order. That is an at sign. A transfer function. A is 1. I think tau is 10. Remember our omega is it cannot be 1 over tau. That's when we'll see our peak. So it should be 1 over tau, which is 1 over 10. That'll be 0.1. Anything else I'm missing? I think it's just k tau, and I have an omega defined already. Pretty sure we did np log space somewhere up here. Right here. We don't really need to we redefine a tau. We're gonna type that in, and then I'm gonna copy paste everything, our amplitude ratios and the like. So I'll actually keep that right now. Real and imaginary. Remember, we just separated the real and imaginary terms from a complex number. We got the amplitude ratio by taking the absolute value or the magnitude of real and imaginary. So if magnitude of a vector, if real and imaginary were the vector components, and then the phase, we unwrap the arctan function so that it would keep going negative instead of popping up to the quadrant, positive quadrant. I think quadrant 1, hopefully. I want quadrants. So yeah, quadrant 1. So it'd be going negative, quadrant 3, and then popping up to quadrant 1. But np unwrap avoids all of that, and of course we convert to degrees. And I think I could just copy paste this figure. So I'll put them all in one spot, and then we can combine them all later. I think I need to update the axes, since that was one other thing. Yeah, this was not in log. It should be in log for a standard Bode diagram, but it works out. Well, it doesn't work out, but it makes it easier to see, since the values are well, they're automatically changed so that it's visually, like, I don't know, appealing. You can see where it ends and starts. Yeah, technically this should be also an update y-axis, so I'll change that. Now we have our second order. We'll do a split screen here, why not? So I'll split this, and where were we? Somewhere over here on the right. So yeah, right there. And then we did the j omega. Did I not do that? All right, here is what I want. So course label A and B. This is what I'll be typing in. So I'll just type it in without assigning it a variable name. It'd be k times, I guess we can do divide. We have 1, I'll do extra parentheses. So 1 minus, and then tau is capital tau, double T, squared. Omega is also squared. So I'll do another one. What else do we have? We have plus j omega. So j is just 1j. That's how you multiply it. Since j is built in, we have omega times 2 times zeta. So zeta was another thing I need to type in, and then tau. I'll define our zeta. Zeta being our damping factor. Is it zeta? Oh, I thought sigma. So zeta is z. Let's make it 0.1. So if it was 0, the angular, the peak would be at exactly 1 over tau. And then I'll run it for now, but I don't think, oh yeah, I need to assign it. So it'd be Ri. The real and imaginary, and then I can change, it looks like a really sharp peak, but if I adjust this in log, then it'll be a very small peak, like we'll see, like we saw, I should say, in class. So I think this is fig 3 or 4. 4. Keep it consistent. What's happening? Oh my goodness. Okay. And yeah, so I didn't update the log axis. And let's do that. But we only want to update the log axes for the y, or the y-axis in log for the first graph. So row equals 1, column equals 1. And that's what it looked like in class. So I'm on main still, so I don't know why I went to screen share. Okay. We have our peak, and remember this peak is at 0.1, almost 0.1. If I change zeta to be 0, it will be exactly at 0.1. So let's try that. Oh, now we have a really sharp one. Is this in log? Yeah. So yeah, it's asymptote at -180. I don't know why I'm focusing on that, but again, two tanks in series. First order transfer functions to define each tank. We have asymptote at -180 degrees, as I've mentioned several times now, and then we pop up to our peak here. It's should be about 0.1. Yeah, 0.1 is our peak, and this angular frequency of about 21 degrees we want to avoid. So that's the whole reason why we did this. We reverse engineered so we avoid the sinusoidal input at 0.1. That gives us this amplitude ratio maxing out at a peak where the derivative was 0. Remember, we took the amplitude ratio to be 0, so we took a derivative equal to 0 is what I meant to say. So at that angular frequency, we want to avoid, since that is our natural frequency, so avoid a sinusoidal input with this angular frequency since it matches our resonance frequency, and this amplitude ratio maxing out at a peak of 0.1, which is 1 over tau. So if I change this, it should shift over, I don't know, 0.9. I'm almost at critically damp here. So yeah, we don't even have a peak anymore. Maybe 0.2, 0.5. They can barely have a peak anymore. So yeah, it's shifted over, not exactly at 0.1 anymore, but something like, can't even see that. So small. 0.5 is too much, I guess. There's our peak. So it's 0.3. But now it's like 0.09. 1.7 is that peak-ish. Already it's unstable, but again, well, unstable for this degree since it can't be unstable if we added that proportional controller, which is simple. It's only a Kc constant. We wouldn't oscillate since we can't reach that -180 degrees, but you can have your amplitude ratio oscillating if you, or you can have a infinite amplitude ratio blowing up if your angular frequency matches this, if it matches this angular frequency, or if it matches, sorry, let me reword that one once again. So if your amplitude ratio can kind of blow up to infinity, it again at this 1 over tau angular frequency, since it matches the natural frequency of the system. But if you have some dampening, like 0.3 zeta, as I have there, it's not quite at 1 over tau. So usually it's the case that we do have some dampening. So that's the whole idea there. And then now I think we move on to the last portion of these series of problems for today's video. Let's see here. Now, we didn't do anything yet. Now we're leaving with the last two here. The pure time delay. So this idea of pure time delay in the Laplace domain, we represent that as e to the negative, so whatever our time delay is, maybe like theta, so e to the negative theta times s, all in the exponent of the e, I guess exponent of the exponent, if that makes sense. So we'll derive that, and we'll also code that out, some copy pasting as usual. So now to the actual portion. Sorry if you're following along to complete these problems like I am, but now is the end of what's technically not required. So here we go, last portion. So we have time delay. I can start with this idea of if we have a higher order transfer function system and we have a input, what we measure that response. So that response to a higher order system might look like something like that, has some curved shape to it. And it eventually bottoms out here at the end. And what most people do if they want to measure this response, what's common in the controls sector or industry, that if that's even the right word, we usually instead of trying to find the differential representing the system, we usually use something called FOPTD. So that's FOPTD representing first order plus time delay. So this idea of, instead of trying to get this, trying to, I don't know, unravel the details of a differential representing the system that's higher order. Instead, we'll do something like a time delay, and then we just measure a first order, something like that. And you can see it kind of approximate this higher order that we had earlier. It kind of looks like that shape. It should. So not quite as a strict curve point here. It's usually more gradual, but hopefully my drawing kind of gets the idea across. So it's instead of trying to get that differential for that higher order system with a response to a step input, we use a first order. So first order usually is, well, it is by definition just an exponential curving up and bottoming out at the end. So you see that here in this portion, and then the time delay is of course when it is 0. So we shifted over our first order transfer function. All right, next is what actually does that look like. So it would be our first order transfer function that we know and love, now s plus 1, and then we multiply it by this time delay, so e to the negative theta s. So theta is our time lag. So it's purely a transfer function we multiply by that is a time delay. And time delay exists everywhere. Nothing is perfect. Nothing is extremely or that fast to, get rid of time delay. It always exists, and it's kind of the bane of all control systems. So let's do that. Amplitude. We need to get that amplitude ratio and phase lag, since we're going to be adding it onto, well, respectively, we're going to be multiplying by the amplitude ratio and adding the phase lag from our first order. And well, I won't show it, but you'll see what's changing. So yeah, we'll do just that. E to the negative theta s. We do our normal substitution, s equals j omega, to get into the frequency domain. So this would be e to the theta jw. And notice that we don't have to multiply by a complex conjugate because we're not dividing by an imaginary number. We don't need to simplify things that far. However, we can simplify this further with Euler's identity. So Euler's number, maybe. We've done this before in previous videos. So this is equal to cosine, if I can type or draw, cosine theta omega, and then it'd be minus since there's a negative sign, j sine cosine theta omega minus j sine theta omega. So that's the, I don't know, function we have to take the amplitude ratio and phase lag of. So amplitude ratio is actually nothing special. If you remember, amplitude ratio is square root r squared plus I squared, real and imaginary squared. So if we do that, we label them real and imaginary. You'll actually notice, well, this is just cosine squared theta omega, then plus a sine squared theta omega, and that is equal to square root of 1, which is just 1. So I notice that the amplitude ratio doesn't actually change. So we don't actually have to change the amplitude ratio by multiplying by something new. It's just 1. So amplitude ratio remains the same. However, the phase lag is where it gets a little interesting. So we have phase lag is equal to tangent inverse of I imaginary over real. And this is tangent inverse rewriting. So imaginary is the sign. So this is negative sign, right? Up here, yep, negative sign. Oh, negative sign, come on. Negative sine theta omega over cosine theta omega. Notice sine over cosine. Well, actually, let's pull out that negative first. So for odd functions, tangent, again, f of negative x equals f of x, or negative f of x. Hopefully I wrote that right the other time. So we pull out that negative, that's tangent inverse of, I'll combine the step here, sine over cosine is tangent, or theta w, or tangent of theta omega, and those tangents cancel out, and you have negative theta happening. Negative theta omega, and we have to, well, in our case, subtract that from, if you remember our original, maybe first df equal to, it was, what was it, negative tangent tau omega. So for time delay, what is happening? Time dd, we have negative tangent inverse tau omega, which would normally only be 0 to negative 90 degrees. we have this minus time delay omega. So now this has a domain of pretty much whatever omega can be. So 0 to infinity, and it's actually negative, so it'd be negative infinity. So 0 to infinity. And you'll see why this is important, since normally, again, negative 90 degrees, we don't oscillate with a proportional controller. That proportional controller, the phase lag of that is 0, since it's, so like, I think I wrote it out already. Somewhere up here. So KC, proportional controller phase lag, no imaginary values. It's just a constant KC, so it's 0. You're adding 0 to our phase lags. So if we had a proportional controller, what I mean to say, there would be no value for that proportional controller where we would reach a instability, since it can't even reach negative 180 degrees. However, now with this negative theta omega term, we're not stopping at negative 90 degrees. We actually stop at negative infinity. So it'd be like 0 minus infinity, or more like negative 90 minus infinity. Like we're going to negative infinity no matter what. So what I mean to say is now there's a possibility of this time delay transfer function, well, first order transfer function multiplied by a time delay, there's a possibility for this to now become unstable, since now we can reach negative 180 degrees with this negative theta omega, which is, may I add, this theta is a multiplicative product to our omega, and omega, remember, we can set that to whatever we want, whatever positive values we want, whatever negative values we want. It reaches negative infinity, and now we'll have a limit to where we can put our proportional controller. So if we multiply in KC, well, it'd be minus 0, since it doesn't have a phase lag, as I mentioned before. And it would just be KC squared over, for the amplitude ratio, it'd be KC squared, maybe something like this. AR KC is equal to square root, so plus I squared, which is equal to 0 squared, and then R squared, which is KC squared. I don't know why I put a R2. And KC squared squared is just KC. So I'd be multiplying by amplitude ratio of KC. That's kind of the proof of what we mentioned. Well, I showed last time, but we didn't really prove it, and I don't think we proved it in class. So again, this amplitude ratio is a multiplicative product of KC. So we multiply the amplitude ratio by KC, and it shifts up or down depending on whatever value KC is and however much we changed it by. So KC, pretty sure we did this in a previous video, but just simplifying or going over it again. KC, if KC is originally 10, and we multiply, well, we decrease it by 1, then the amplitude ratio will decrease by a factor of 1 and actually shift down by a factor of 1, or not 1, 10. I don't know what I'm saying. 10 to 1 is a factor of 10. You're dividing by 10. So you'd shift down 1 for the amplitude ratio, since that's in terms of log. And while I'm on that tangent here, remember, for amplitude ratios, we have something like this. And if we're multiplying our transfer functions, we actually add up the amplitude ratios. So if we had G1 and G2 from earlier, the G12 I mentioned earlier would be something way up here, maybe, since we're just adding these two up, because we are on log scale. That's what it would look like. So anyways, I think we can just graph this out, right? So it is e to the negative theta j omega, and I'm not sure what we put for theta. Remember, maybe like a small delay of like 0.1. We can try it out. Anyway, we'll see that now the first order transfer function can be unstable. So honestly, same thing. Might need to put the omega, since it might be too far out. So I'll comment it out, but I'm pretty sure it will go out further than we need it to. Just to check it works, I won't store it just yet. Then we copy this for our graphing. well as twice. Well as getting our amplitude ratios and phase lags. So this is Fig 5 now. Yeah, so I think it's I'll put in a theta. Theta is equal to 0.1 maybe. So that's our time delay. Not k equals, so do I want to put a kc now? I can put it in later. So kc is equal to 10 maybe. We'll see we have a upper limit for kc at that instability. So k, what was it? K, the time delay was np exponent, right? Yep. And then we have negative theta. What is that? Negative theta s, which is j omega. We do the s equals j omega substitution, so that's 1j times omega, and then we divide. What did we divide by? Just tau s plus 1, right? Tau, so tau j omega 1. Check. Split that. Did I not even write it? That's kind of funny. Yeah, we'd multiply these two. You can see my cursor. We'd multiply these two. Block diagram algebra. So it's just tau s plus 1. So that should be enough. It isn't. Oh well. So let's see if this actually runs. Yep, we got our real and imaginary, so we'll store those. I'm reusing the same variable names, which you shouldn't do, but yeah, this is just kind of to show what it looks like. So yeah, we have way too many since we're going out too far. So let's decrease our angular frequency here. Let's go -1 to 1.5 maybe. There we go. And now you do see we are hitting -180 degrees versus, did I show it here? This is second order, so you bottom out at -180 degrees. Can I combine these? Yeah. I'll show first order right here. Do we have one already? These are 3. So where am I going? I don't know. Okay. So this will be let's do a first order. Keep everything the same. We don't need a zeta. I can just copy paste the first order down here. Just remove the exponent. Where am I? Here. Right there. Remove the exponent. And Fig 6. Yeah, we don't even reach. Yeah, right there, -89. If we go further, sure, why not? I'm gonna change the omega. I keep moving omega around. Let's put it here. We go to -1, 2, 3. No matter how far we go, we never hit that -90 degrees, so we can never be unstable. Our amplitude ratio, even at lower or higher frequencies, not reach 1. Good. Moving on, and again, that's what the controller. So even if I added a controller, no matter what amplitude ratio we had, we're not at -180 degrees, so it doesn't matter. Same thing for second order here. Is it second order? I think. Where is the second? Did I delete it? Up here? Yeah. This is 3, right? 270. So this is 3 in a row. Did I not do 2 in a row? Well, I can just square it, right? Was it squared or was it -1/2? Is it worth doing? Already here. Sure, why not? Where are we? So we want the amplitude, or we want the transfer function of 2 in series. I'm pretty sure I did that. 2 in series. So it just, oh, it's just k1, k2. Oh, this thing, s squared. It's, yeah, I did second order, didn't I not? That was this thing. Yeah. But it is hitting 270, which I'm confused about. This correctly? I might have not typed this correctly. Okay. Oh, this is our exponent. What am I talking about? I'm getting so lost. Did I just not evaluate it? There we go. Got 180. I don't know what happened. It just disappeared. So this is our second order. We typed this out already, and it's technically second order is the same thing as two first orders in series. So bottoms out negative 180 degrees, but it's an asymptote, so it never actually reaches negative 180 degrees. Therefore, if we added our KC proportional controller, no matter what we do, it'd always be stable. Now, here's where it gets funky. This is our, what am I doing? Time delay, right? Time delay. So this is time delay. F. Did I rename this one to first order? Yeah. Okay. So now our focus with all these graphs. I can combine these, right? So merge. Oh, I merged them and the graph went away. That's what happened. So now we do hit negative 180 degrees. So now whatever this frequency is, so it's about 15.7, 16.68, 15.7, 16.68. So about here, we're at 0.00565. So now, thank goodness we're not at our, oh, how am I still split? Oops. So right here, about 15 to 16-ish, we're at 0.005, 0.006. So we're not at 1. The amplitude ratio is not at 1. So we're not unstable. However, if we increase our proportional gain controller, our KC, by a factor of about 100, we will be hitting that limit. So we'll add in KC here. Remember, KC is just multiplicative of amplitude ratio. I showed that earlier. So we have KC here, and it adds no phase lag. So still be the same. 180 degrees, about 15 to 16-ish, maybe 15.7. Now we're at this. Did it even update? Haven't. KC 10. Well, now we're at 0.0. I don't know, I must have miscounted a 0, so let me bump this up to, oh, I didn't even change it. It's at 10, so do 100. 15 point-ish. And now we're at 0.6, so cutting it pretty close to amplitude ratio of 1. If I make this like 500, it'll reach 1 for sure, right? 15. Yeah, we're at 2, so already greater than 1 at the same frequency, about 15.7. So that's an amplitude ratio of 3. 15.7 is about our 180 degrees. So now you see this upper limit of 500. I know, kind of egregious for a proportional gain of what we've seen, at least in our examples, but now it does exist for this first order transfer function. Normally, again, before we bottom out at negative 90 degrees. So no matter, I can add a, well, I don't think you'd see it. Well, I can try. It would just change this amplitude ratio, but we'd never have a negative 180 degrees here. So it wouldn't matter in the first place. Yeah, it would change. Is it worth? Nah, I don't think it's worth showing, since again, amplitude ratio is multiplicative. It'll just shift this graph up or down, and no matter what amplitude ratio it is, if it never hits negative 180 degrees in the first place, then it's still stable. So I think that is the end of our series of problems here. So yeah, we showed that with time delay, and everything has time delay. So now you can see there's this upper limit for controllers but that have time delay. So yeah, and it becomes unstable with proportional only control. Yes. So now we have an upper limit with that first order transfer function with time delay, and normally that's also used to approximate higher order systems in response to a step input. So yeah, kind of discussing transfer functions in series, how they the domains of them for at least first order is negative 90 degrees. Then we had showing over damped second order, so it was greater than 1 for zeta. And then we actually did the second order as well. We showed that it had a peak to avoid that amplitude ratio maxing out when the dampening was 0 and the angular frequency was the natural frequency, so 1 over tau in this case. And that avoided, if we found the amplitude ratio at its max, we could find the natural frequency and avoid having a sinusoidal input with a frequency that matched that natural frequency. Then we did the phase lag with for pure time delay. So it was negative theta omega, I believe, and then that allowed us first order transfer function, which was originally bottoming out with a phase lag of negative 90 degrees. Now it bottoms out to negative infinity, and now we have a negative 180 degrees condition fulfilled. So now that amplitude ratio is something we have to watch out for. So we have an upper limit on that proportional gain if we multiplied in RKC, since amplitude ratio is just multiplicative of RKC for that proportional gain controller. And we graphed all of those. So I don't even remember what was behind this. So was this even important? I think it was just axes. Yeah, axes and inputs, nothing crazy. But I didn't need it. It was all in here. So gotta say that was pretty good. Okay. I'll switch off on the collab and I'll leave it here. So yeah, thanks for watching.